Very well. So thank you everyone for coming today, joining us on this this new edition of TRACCS web series. My name is Andrea. You've probably met me before. Today we're going to listen to Transmission Dynamics team talking about trains with brains, the future of infrastructure and rolling stock monitoring. So before we actually start our talk, I would like for us to go over some upcoming events. In case you haven't heard, TRACCS is organizing a Canadian Transit Rail delegation to the Czech Republic. This is exclusive for TRACCS members, and the purpose is to share best practices between the Czech Republic and Canada. If this is an opportunity that you'd be interested in, please email Jen Bazansky, jenb@traccs.ca or at info, and we'll be happy to connect with you and give you information. Another big event that's coming up, as you already may have heard, is TRACCS Rail Day. This year will be an indoor-outdoor event, and we will even have a conference, 2 days, 3 rooms with several industry leaders. We're looking forward to seeing you all here at the International Center on June 2021. If you're interested in the speaker schedule, you can now see it online, traccs.ca/2023 conference. Our keynote speaker is Rick Leary from TTC. And we have to thank our sponsors, Margie Straub, Platinum Track Service, PNR Railworks, A&K Railroad, Holland, Siemens, Stantec, OWS, NGE, and QMP AirTech. Without their support, our work would not be possible. So, as I said earlier, today we're here to listen to Jenny Hudson and Jared Rosinski from Transmission Dynamics. I'm here with Alosha. Alosha Paranavitana is one of our assistant directors at TRACCS. Alosha, how are you doing today?
Hi, Andrea. I'm doing well. Thank you for having me here. I'm looking forward to learning more of trains with brains, transmission dynamics. So a little bit about myself. As Andrea mentioned, I joined TRACCS just at the beginning of this year as Associate Director. My background is more in training and development, as well as facilitation and anything training related. I dove into the railway industry about 5 to 6 years ago, and I've loved it ever since. So when it comes to this webinar, with Trains with Brains, Transmission Dynamics will talk more or less specifically about their dynamic tools when it comes to delivering world-class Internet of Things solutions to complex industrial challenges. So the future of infrastructure and rolling stock monitoring, that's something that will be discussed today as well, powered by our AI, artificial intelligence, and machine learning, redefining the status quo of next generation rail asset and rolling stock monitoring. Our presenters for today will be Jared Rosinski and Jenny Hudson. They're out in the UK, so kudos for them for helping us out here in the webinar at 5 p.m. over there. A little bit about Jared. He has about 20 years, more or less, actually over 20 years of experience when it comes to machine dynamics. He is the CEO and founder of Transmission Dynamics. And with Jenny, she's done quite a bit when it comes to supporting SMEs to grow through innovation, and has been with Transmission Dynamics since the fall of 2020. With that being said, I'll turn it over to Jarek and Jenny to take us away.
Thanks so much, both. Thank you. Thanks for having us. Jarek, did you want to say a hello while I share slides? Oh, we can't hear you, Jarek. Don't worry, you sort your mic out. I was starting anyway, so what I'll do is just to introduce everyone firstly to the company, just take you through a little bit about us before I hand over to Jarek, who will give you kind of the technical content of the presentation. Hopefully you can see this now. I am just leaving it on the sideline so that Jarek knows where I'm passing on to him, but hopefully that's nice and big for you to see. So thank you again for having us as part of the TRACCS webinar series. We are TRACCS event attendees and very honoured to be with you all today and sharing the information on Trains with Brains, which is essentially our product portfolio that we offer to the global rail market to support infrastructure and rolling stock monitoring. As I said, just briefly for a company introduction, we were formally established back in 1996, following a background of Jarek setting up the company and undertaking consultancy-based troubleshooting of huge industrial assets around the world and across all sorts of sectors. And that troubleshooting we realised wasn't scalable, done through Jarek and himself. So we started developing the technologies that we could embed our knowledge into to extract the data we need to be able to inform asset owners and operators about the condition of their assets. We are based in the northeast of England, and we have a second office in Poland, which does our sort of software and embedded systems work. And together we have over 50 employees now with all of those disciplines you can see on the screen here. And that's really important for us because typically in our type of business, you would expect companies to specialise in either the hardware of the sensors that we develop or the software or the data analytics. And actually what we do is everything from design to development, deployment, and then analysing the data and monitoring the assets. So we do everything under one roof, which keeps us really fleet of foot, allows us to continually develop products to meet the market's needs at a much quicker and effective rate than you might see elsewhere. So as a company, we offer all of these things on the left-hand side. As I said, we've got the hardware of the sensors and data acquisition systems, the means by which to transfer data. We have, most importantly, this human-derived engineering analytics that is the foundation of everything that we do. It's about transferring our knowledge, experience, and intuition into silicon-based electronics and beautifully packaged and easy to install hardware. And then, of course, we apply artificial intelligence. So to be able to accumulate all of the data that we have at scale from all of the devices we have across the sectors around the world and look for patterns and anomalies that we wouldn't be able to see with the naked eye. And then, of course, have cloud-based automation so that the information or the intelligence that we've got goes immediately to asset owners and operators when predefined thresholds have been met. As I mentioned, we do work across all industrial sectors. These are the key ones that we're working with today, with rail being one of our top three. Obviously, huge opportunities in the rail market to support efficiencies, bring down operations and maintenance costs, reduce kind of boots on ballast, as we call it in the UK, having physically walking up and down track looking for faults, improving safety and reliability. So yeah, we do a lot with the rail sector, right from designing concepts that they come to us and ask for, to scaling up the deployment of some of the common technologies for the greater good of the market. This is our business premises, and as I said, we've got all of those multidisciplinary skill sets as well as the specialist facilities all on one roof. So we even do all of our own PCB population for the electronics. It all happens in-house. And again, that really helps us to be fleet of foot with both development and deployment of the technologies. This is to give you a feel for the clients that we work with. This is just a snapshot. It's not an exhaustive list, but it gives you a feel for the size of companies that we're working with right across supply chains and all industrial sectors. And we are award winning. Just a couple of recent rail awards. So I thought it was worth noting for today's presentation for, I guess, a little bit of credibility for our, talking about this subject today. So just earlier in the year, we were Innovation of the Year winner for the Rail Business Awards, which is a national UK award ceremony, long-standing. And that was for the work that we did with Network Rail, who is our infrastructure owner and operator in the UK and one of the leading rolling stock leasing companies for the Trains with Brains technologies that we're presenting today. And the other Venture Fest on the bottom here, the orange brain, we got the Advanced Manufacturing Innovation of the Year award, again for the technologies that we've deployed for the rail sector. So hopefully that sets the scene nicely as to who we are. Jarek, how's your mic doing?
Well, can you hear me okay now?
You're back, smashing.
Fantastic.
Just before you start, Jarek, we just thought we would run the 2-minute video so that we can sort of set the scene for Trains with Brains. I'm actually just going to, excuse me while I stop sharing. We had a bit of an issue in the dry run with the PowerPoint sharing the sound, so I'm just going to switch across to YouTube and run that separately. Excuse me. Give me a shout if this doesn't come through.
It came through, but there's no voice, Jenny.
No sound?
No sound.
Oh, apologies. We might have to give that one a miss then, but we will put the link into the chat. It's only a 2-minute video and it just summarises what we're presenting anyway. But we just unfortunately seem to be having a technical issue with sharing it. So I'll pop it into the chat at the end of the session. In that case, I will hand straight over to you, Jarek, to please give us an overview of the Trains with Brains products and the sorts of things that they are achieving for the rail sector, please.
Thank you very much, Jenny, and I hope that I can take you for a very interesting journey, which will be highlighting our mindset, how the future rail monitoring systems would look like. We will be doing a lot of emphasis on artificial intelligence and machine learning. I know it's topical. I know that everybody is talking about the AI, ChatGPT. Some of those applications may be not suitable, but some are. And then I will be talking about how fantastic support from machine learning, convolutional neural networks, and AI we are already embedding, and how powerful those systems become. So Trains with Brains, that name we kind of like very much, because we are postulating that all future rail way monitoring services will be running on the trains. So it will be very much train-borne instrumentation, which becomes less expensive, far more powerful, and it can be fitted on routinely operating trains, which means that we are scanning the rail infrastructure number of times per day, maybe dozens of times per day. So what we are doing there is we develop this portfolio of various products, and I will start from the very top. And at the top of the train, on the roof, we mount that Pandas V camera that is sitting bolted to the top of the train, and it's a very intelligent device, requires only power supply from the train, 24 volts. All the rest of the very advanced electronics, data crunching, camera recording, artificial intelligence and analytics is embedded in that camera. That camera has got a wiper, Bluetooth communication, 5G communication, it's got a GPS, GSM, the combined antennas, and that communicates with the wireless accelerometer. On the right-hand side top corner, we've got this tiny device, which is just simply clamped on the pantograph close to the overhead line. That in its own right, it's a very small but powerful accelerometer, XYZ, which goes equipped with a Bluetooth communication, which is powered by embedded coin cell battery. It's very light, unobstructive, and it's powerful. Now, just to put into perspective, that accelerometer powered by the coin cell battery will be running for more than 2.5 years before we need to change the battery. So I think that just by eliminating any wires, any power supplies, running the connectors on the pantograph frame, we are effectively making that system incredibly easy to deploy and very easy to maintain. Now, as we go clockwise, under the trains, we are proposing, and we're already deploying, smart bugs. Smart bugs are very tiny devices. They are not very much bigger than the button of the code. And again, the mindset there is to have this future-proof self-learning tools, which have sensors embedded internally in the smart bugs. There is a battery supply, coin cell battery, and the wireless communication, again, to the gateway. Those smart bugs are glued to the structure, whether this is axle boxes, whether this is bogies, the electric motors, the bearing assemblies. It's all very quick and easy to deploy. We refer to those smart bugs as sprinkling the sensors because they are so easy to deploy, very small, they are powerful, and they do quite a lot of diagnostics and monitoring in its own right. And then the final product there is the Smart Oil Plug. Smart Oil Plug is a direct replacement of the existing oil plug in the final drives. And then the installation is, again, very simple. We simply unscrew the existing oil plug, oil filler or oil draining plug, place the smart oil plug in place, and that smart oil plug at the bottom is got the circuitry which extracts the ferromagnetic oil debris, just like any other typical oil plug used in rail industry, but also it measures the amount of the ferromagnetic oil debris which is attracted. So we measure the volume, and internally is fitted with a battery, wireless communication via Bluetooth, and also XYZ accelerometer and the temperature sensor as standard. Now, set of those sensors become very powerful. Although they are containing only accelerometer, temperature sensor, gyroscope, the amount of data analytics which we'll describe in a moment, it's simply eye-opening. So if we go for the next slide, when we go into more details, we've got this camera at the top, mounted on the roof, and roughly in 2021, which is 2 years ago, we deployed those systems as items working in tandem. When accelerometer detects the impact, it requests the camera to immediately freeze 5 seconds of the video recording before that impact and continue the recording for 5 seconds after the impact. We pack then that's 10 seconds of the footage and send it to key stakeholders within the next 1 minute. So following the impact, the key stakeholders would immediately have the information. What caused that impact? Is it the dropper wire? Is it the strong registration arm hanging? And is there any other reason, like the birds which are flying into the pantograph, causing similarly very high impact? The camera on the right-hand side has got the wiper scraper, which is designed to make sure that the system is completely maintenance free. So we have sapphire glass windows, so the scraper wiper is not digging the hole through the standard flawed glass. And we've got a built-in microphone, we've got obviously 5-in-1 antenna and unprecedented internal artificial intelligence and signal processing and data recording on board. If we go further down, we've got the system architecture is very simple. We have accelerometers communicating with the camera. Camera is acting as a gateway. The remote access via 3G, 4 or 5G network communicates via the firewalls with the externally mounted clouds. So from the accessibility point of view, from any location, any mobile phone, any device, we can interrogate those systems and receive also automated alarms as the signals indicate very unusual operation. If we go for the next slide, here is the installation in the flesh. We can see that the roof-mounted camera is on the left-hand side. It's just a standard replacement of any classical Schuber and Huner antennas. We simply drill the hole, and then from the bottom we supply the power. Otherwise, the system is completely sealed like any other rail-approved antenna. Now, the automated reports, which are generated by the system, are truly automated. We have no engineering staff overlooking to produce the reports. As soon as there is an impact, as shown example on the right-hand side, we send the video footage shown on the left-hand side, 10 seconds, and also stamp the exact location within 2 meters accuracy to show exact position where the impact occurred. The next slide, please. That shows the example of the pantograph running, and then on this occasion converging wire causing the impact. We play that video back and forth just to show how significant impact there is if the converging wire height is not set correctly. All those events we are monitoring, sending the videos and the footage. This slide shows a typical event which we've seen before. On the right hand side we see the arcing. So the machine learning on board detects the arcing, detects the dropper wires, detects the tracking of the overhead wire, which is stagger, and the pantograph height. The next slide shows a classical event as we have the misaligned neutral section isolator. According to Network Rail in the UK, that particular case was misaligned from the first day of installation. Incorrect installation, which was there causing continuous risk of dewirement until Panda's system was installed and detected within the first pass the issue with the application. Right-hand side top insert shows the location. Probably the most interesting events which we are capturing are dropper wires, and the dropper wires are interesting because they can cause directly dewirement risk. When the overhead wire is lifted up as the pantograph approaches, the broken dropper wire can wrap around the pantograph head and then take off the pantograph off the roof, or alternatively the pantograph will take the overhead wire down. Those incidents are very costly. In the UK, there are around £1.5 million to clear the fault, and we detect things like missing dropper wires, broken dropper wires which are hanging just at the single strand of the wires, shown here when we reported that the team from Network Rail would report on site within 2 hours to immediately cut off that dropper wire to ensure that the replacement will be carried out in due course and avoid immediate risk of dewirement. Another one here, the slide shows the detached jumper wire. You can see that the bolting arrangement from the bottom holding the catenary is simply detached. All those events are continuously detected, reported using the on-bourn analytics. Here's a very unusual event which was captured. That event occurred during the Jubilee weekend last September, when clearly there was an act of vandalism, somebody dropping the wooden post, 100 by 100 millimeters, very heavy wooden post, clearly aiming at the driver. The drop was missed by a few milliseconds, and then we actually impacted the pantograph. This is the video which shows that moment captured, and the British Transport Police was informed about the incident, immediately taking action. Classical events of the arcing. Plenty of those events in some weather conditions or winter, when we have the icicle forming or freezing rain forming on the overhead wire. The wear to the pantograph head, to the carbon, can be accelerated by 100 times. So here we go, from the pantograph carbon living there for around 3 months. Typically, we may shorten that to just a few short days. We are detecting birds' nests. They cause the safety implication in their own right. The bird's nest like that can be formed within 2 or 3 days, and the regulations are, if they are closer to the overhead wire than 600 millimeters, they need to be cleared because of the potential safety implication and bridging the 25 kV to the ground. Here we've got a classical event where we have the bird strike, very unpleasant, side effect, collateral damage of the train operating at high speed. We can see on this occasion that the bird struck the pantograph. Not that those events are critical to Network Rail, but obviously accelerometer records this strong impact. Camera records 5 seconds before, 5 seconds after. We aim and then find that this is the event which Network Rail don't have to service, but they need to inspect the pantograph, because with the heavier birds striking the pantograph, they may cause significant damage to the pantograph itself. Here, there are some quite difficult cases to detect, and if it wasn't for the accelerometer, those cases would be frankly undetectable. On this occasion, you can see that the registration arm is being lifted due to uplift as the pantograph presses the overhead wire with a force, say 100 Newton upwards. And when that happens, that registration arm on the left-hand side is actually impacting against the horizontal pipe. And when you inspect the line by using the standard visual inspection, you would not be able to detect that there is a very strong impact associated with this setup. Clearly detected by the accelerometer, filmed, and then forwarded to Network Rail, who analyzed the data in closer detail, realizing that's the case which requires immediate correcting corrective action. Wire stagger and the pantograph height reserve a special interest, because wire stagger typically is designed obviously for the overhead wire to traverse from the left to right to result in a very even wear of the pantograph carbon. But if there is a terrain subsiding and the mass holding the overhead wire gradually tilt, that stagger will be gradually shifted from the central position to the left or right hand side, and then monitoring and continuously trending wire stagger is absolutely mandatory to detect the potential of the overhead wire moving along the pantograph carbon to such an extent that eventually the wire is trapped under the horn, which means, again, either pantograph being taken off the roof or dewirement occurring unquestionably, obviously, if the overhead line. But the thing about this analytics is that all of this, what we are seeing here, drawing the binding box around the pantograph, detecting the exact point of intersection to continuously monitor wire stagger and the pantograph height, as shown on this graph here, is carried out between each and every video frame. So that's where the artificial intelligence kicks in, the machine learning. We've got a number of those algorithms, and with a very high processing power, we are effectively continuously automatically mapping the overhead wire stagger and pantograph height. This is actually showing here a classical example. We've got the zigzag line. You can see that the lower graph, 0 is the center of the pantograph. 1 is when the overhead wire slides to the right-hand side, -1 to the left-hand side, extreme position of the carbon. So you can see that on this occasion, we've got slightly biased center of the overhead wire towards the right-hand side, and then we almost touch the end of the active pantograph carbon. You can also see somewhere in the middle of that graph where as the converging wire takes over, but it's beautifully shown the zigzag line, which is equivalent to the stagger, which is intentionally designed to result in the pantograph even wear. The next slide is showing some even more critical events. I mean, on occasions, very rare occasions, fortunately, we have heavy rain, which may result in the landslide. When there is the land sliding, it may take the rail with it, and as a result, we may actually have a very strong risk of derailment, not dewirement. Now, this detection of that is done by the sway detection. What we have on the camera, we've got the accelerometer, XYZ, and the gyroscope, and the camera, which is mounted on the roof, acts almost the same way as the pantograph-mounted accelerometer, with the exception that it registers the position of the carriage. And we are continuously mapping that carriage movement. So if we have a strong sway event, and that's the time when our coffee is spilled on the table, we are monitoring that. Here, this graph shows a classical event. There is something like 23 files superimposed on each other every single pass, and you can see how repeatable the carriage sway is in this location. So X, Y, Z acceleration measured here, and you can see that the 23 passes of the train are resulting almost like a one single pass with a repeatability which is outstanding. Good news about the high repeatability here is that by establishing the baseline of the signal, we can very easily detect deviation from the baseline, and that's where we are reporting deviation from the baseline. The next slide shows the classical clustering of the event and reporting. There's a classical implementation. Probably everybody in this space does similar thing. You use the Google Maps, and then on the Google Maps, on the positions maps, you incorporate dots. Larger dots means larger number of events, and then when we zoom onto those events on the right-hand side, you can see how many of the exactly the same impacts occurring roughly clustering in the same position, just approaching on this occasion overhead gantry. So this is all continuously reported and documented on the global data network. So our clients have access to the global data network, and at any time they can inspect the progress or elimination of some of those faults as the infrastructure is repaired. The next slide shows the various system options. Jenny, is it okay if you discuss that, please?
Yeah, of course. So essentially, there's 3 different options for the PANDAS system, the PANDAS vision system. PANDAS wireless is just the impact detection, so the accelerometer up on the pantograph head reporting significant impacts by email and text messages. PANDAS vision is the same thing, but with the video camera, so you're getting the footage, the 10 seconds of each of those impacts. And then the advanced analytics on the right-hand side here, it's the same hardware as PANDAS vision. It's got the camera and the wireless accelerometer, but it's using that video footage to give these enhanced measurements as well.
Thank you very much, Jenny. Now we are on to the smart bugs. Well, that's our registered the design, which is effectively describing those small devices. They come in various shapes and forms. Typically, they are round devices powered by the coin cell battery. Sometimes we manufacture square packaging. On the right-hand side is a bigger version of exactly the same device, which is powered with the C size of the battery. The beautiful thing about those devices is that they're small, they are collecting data, they're intelligent, self-learning, we've got a duplex communication, so any data collected and analyzed will sometimes result in improvement of the process. So we are into this very elusive operation where we are injecting into the systems perception or planning, which is typical to artificial intelligence. Those systems may and will change the sampling rates, how often they change, they wake, they report, depending on the information they acquire. Very intelligent, very easy to deploy. As I mentioned at the start, they are deployed using the magnetic attachment when we use on the right hand side bottom insert, which is just used for a few minutes when the adhesive is setting. Otherwise, there is a standard operation from -40 to +85 degrees C. They come with a ±16 G and ±200 G acceleration range. They can be equally successfully used for the pantograph monitoring, for the axle box detection, various issues from bearing failures to hot boxes to wheel flats and the rolling contact fatigue. They can also be used to be placed on the motors, final drives, and they are really truly powerful devices. The next slide here shows attempts, which are very successful attempts of correlating the interaction between the rail and the overhead line. We very rarely think about that, but when we analyze the signals more closely, we've realized that some of the pantograph events, which are triggered by the rail way features when we go over the deep, and the entire carriage, the dynamic motion will result in the impact-looking character of the acceleration measured on the pantograph. So here we can see the clustering of the events which are triggered by smart bugs, by smart oil plug, by the pantograph-mounted accelerometer, and by the gateway. Gateways are a camera, or gateway is used in slightly different implementation for the smart bugs, and the gateway in its own right has the accelerometer and the gyroscope X, Y, Z to detect the carriage or bogie movement. And the combination of the effectively fitting the sensor from head to toe, which is effectively our trains with brains proposition, is very powerful. When we look at those applications, we can actually see the future very gradually evolving, because those sensors become significantly more powerful. They consume significantly less battery consumption as the technology develops, and they become significantly more powerful as the time marches on. So this is unquestionably the future of rail monitoring using the train bone infrastructure. Now, rolling contact fatigue is a classical example where the smart bugs are deployed on the axle boxes on this occasion. They detected the events which are associated with the rolling contact fatigue. Now, RCF is quite critical for the rail axle sets, because once it sets, it's very rarely arrested. Typically, rolling contact fatigue will be deteriorating. And then we are now able to detect rolling contact fatigue at the very early stages. And this is a classical example here, where in February this year, we detected rolling contact fatigue, we reported that, and then the train was removed from service, the axle tire was turned, shaved to bring it to the good condition, and you can see the result on the right hand side. On this occasion, we are looking at the main axle harmonics, on this occasion from 5th to 10 harmonics, which become very sensitive to the rolling contact fatigue. All of that is reported by either smart oil plug or the smart bags mounted on axle boxes, detecting wheel flats, and on this occasion, obviously, rolling contact fatigue. The next slide shows the tiny pitings, tiny pits, which are photographed on the right hand side, and the effect of those pits, which are being picked up and reported by the smart bags. You can see the multiple impacts on the left hand side, which are absolutely and clearly identifying as small features as shown on the right hand side. The next slide shows the deployment of the smart bags on the electric motor, number 7, and on the fabricated structure of the final drive. This bugs, number 9, 7, and 11, are shown here during the process of gluing. Obviously, the brackets are removed, and then so far, we haven't actually lost a single smart bug, in spite of the fact that we are using the structural adhesive. With a very modern and strong structural adhesives, the bond of bonding those 30-gram weighing smart bags is very, very secure. So on this occasion, we are measuring modulation, and once we measure modulation, we can demodulate the signal using Hilbert transform to detect which part of the modulation is caused by the torsional vibrations, which is frequency modulation, and which part of vibrations is caused by amplitude modulation. That is typically when we have eccentric shafts or missing bolt, so the process of identification becomes very powerful. The next slide, please, shows the smart oil plug. Smart oil plug is exactly the smart bag, with the exception that it contains the oil debris detection and measurement system. So it's not one of those typical oil plugs which detect that there is a short because of so much ferromagnetic oil debris accumulated. We are measuring the amount and continuously reporting that. That's shown on the next slide, I believe, when you can see in the center graph how the oil debris is gradually increasing, and the installation shown on the right hand side, the oil plug, shows this classical kind of dome of tiny ferromagnetic particles which are attracted by the magnet. They are always there, whether we like it or not. Even the small asperities left after grinding will be removed during bedding in periods, so there will be always some tiny amount of ferromagnetic oil debris, and we are monitoring that. We are not responding to that because that's normal. We are responding when we see sudden increase of rate of generation of the ferromagnetic oil debris, and that is the time where we are pressing the red alarm button and report that to the key stakeholders, because that usually means accelerated pitting on the gear flanks, or maybe problems with the wear of the rolling elements. The next slide shows the entire accolade of various measures which we are detecting and reporting in a very powerful way. So initially, when we deployed the smart bugs and smart oil plug, we thought that they will be reporting what's inside the final drive, and we were very conservative on this occasion. We are now detecting vibrations, temperature, oil debris, train speed, gear quality, pitting, tooth breakage, obviously oil loss, wheel slides, track quality, carbon shaft failure, engine misfiring, when we have classical occasional torsional vibration caused by the cylinders misfiring, bent shafts, bearing seizures, damper failures, and the wheel flats as standard. The next slide shows the classical implementation, very easy installation. The smart oil plug is simply replaced from the final drive within minutes, and we're up and running. obviously somebody will immediately challenge that, saying, well, how about the gateway? And obviously we need the gateway. Obviously we need that device, which is shown here at the top, which is talking to smart oil plugs or smart bugs, and that is equipped with the GSM, GPS, and the Bluetooth communication to ensure that we've got full communication with the cloud, including the GPS stamping and geolocation capabilities. The next slide shows a very simple outlier detection. So if we are measuring peak to peak versus RMS of vibrations as a simplest possible subset of the measurement, and we get far more advanced than that, even based on the very simple peak to peak versus RMS for number of final drives, you can see that there is an outlier surrounded by the red box. That is so easy to pick with the naked eye, and it's very pleasing because once we detect and involve the convolutional neural networks or machine learning, we have significantly more advanced way of detecting outliers than just looking at RMS and peak-to-peak values. The next slide shows the wheel flat. Classical example is the photograph showing the wheel flat created when we lock the wheel when this train is in operation. So the wheel will be sliding and generating classical wheel flat. The event which is obviously causing a concern because that wheel flat results in very strong impact in the wheel-rail interface, and also the risk that due to acceleration, when we are just losing the contact at high speed between the wheel and the rail, will be resulting in the angular acceleration and deceleration, and that's how the rolling contact fatigue is spreading around the circumference. And the simple detection of the wheel flat is shown on the right-hand side when we've got classical impact once per wheel revolution. For those who are riding on the train occasionally, you can actually hear that happening occasionally, and you cannot mistake that by anything else. This is a wheel flat. We report those immediately following the occurrence of the wheel flats. The next slide, please. Oh, that is the slides which I'll pass over to Jenny just to close up and ask for questions.
Thanks, Jarek. Yeah, so that's quite a whistle-stop tour of a range of technologies that, as I said, are already deployed here in the UK and around the world and having a really big impact on the rail sector. So we'd really just like to leave the last sort of 10-15 minutes to give people the opportunity to ask us any questions. Perhaps you're curious about the individual technologies or the applications, or even comments on, you know, other things that need to be resolved in the rail sector. We just really welcome any interaction at this stage.
And we don't want to hide any questions or ask to raise the hands. Please break the silence and just ask the questions. We are happy to improvise and answer those questions as they come.
Very well. People are a little shy. While people start figuring out like their chat, where you can type in the question or you can raise your hand, we received a question from, Mubashir Sayed has a question. Go ahead, unmute yourself.
Hi, thank you for the presentation. Very interesting. Like the two applications that you spoke about, I was just curious, in your implementation or the sensors that you offer, do you see any applications from inside or from the interior of the vehicles itself, of the rail cars? Do you have any applications or part of your sensor portfolio targeting those applications?
Maybe I will take it, Jenny, if this is okay. I mean, obviously, once we are inside a vehicle, it's us, passengers, sitting on the chairs and then enjoying the ride. Now, those systems can directly be used to be mounted in the vehicles for the ride quality. So if we are detecting sway, this is exactly what we are doing with those systems. We're looking at the low acceleration levels when we are looking at the axle-mounted equipment. Typical accelerations are plus minus 50 G. We measure plus minus 300 G on occasions, unfortunately, on some stretches. When we are on the bogie, it's plus minus 10 G approximately, and once we are in the vehicle, it's plus minus 4.5 G. So obviously, acceleration levels in the vehicle itself, the carriages are much smaller. They can be used for the ride quality, but not only. In fact, we were recently looking at the application where on the monorail application, there is a need to detect the flat tire. Flat tire can be actually quite dangerous. There are systems which are servicing flat tires, but those systems may potentially fail. And as a secondary system, flat tire measurement will be looking at the mounting accelerometer in the vehicle, and with the sensitivity and the very well-defined frequency contents of the flat tire, one could potentially successfully detect the flat tire. So there are applications, but they are mainly related to sway detection, ride comfort, and potentially some peripheral applications. Is that answering the question?
Yeah, thank you.
Thank you for your question. Someone who had to drop off the call left us a note. They are asking, do you make a distinct separation between the terms artificial intelligence and machine learning in your applications?
Yes, we do. Absolutely. Machine learning is the part, obviously, of AI. Machine learning is an easier part in many ways. I mean, classical machine learning application is when we are labeling the video recordings, and then we are labeling each frame. And then we are using convolutional neural networks to, following the way labeling, detect successfully some features. So it may be, for example, drawing the binding box around the pantograph. That's what was demonstrated. And then detecting the cross-sectional features between the pantograph carbon and the overhead line. And that's how we detect that dot. That's machine learning. We find it easy, or relatively easy. That's how the Tesla cars are continuously improving their successful detection of the objects and the self-driving capability. Artificial intelligence got a much wider and broader connotation, because that's where we are coming into that elusive world of what we human beings are good at, yeah? Or at least we think we are good at. So what is happening there is, it is relatively easy to incorporate CNN, convolutional neural networks, in the computers, but it's far more difficult to inject perception, planning, jealousy. Not that we want to provide that in the machine, but it is very difficult. We can pre-program behavior of the machines, which would look like being intelligence, but to pass over the true, genuine intelligence is far more difficult. And that is the main distinctive difference between machine learning and the pure artificial intelligence. So if we compare the ChatGPT, for example, which is now notoriously powerful in drawing human-like conclusions, and very soon, if not already, being able to replace our solutions, because every single time we propose some clever solution, ChatGPT may actually, or the future artificial intelligence in the broader context, propose the much more powerful solution every single time. I mean, that is the distinctive difference. And obviously there is a very strong competition in the world, because whoever cracks truly the artificial intelligence, the ChatGPT is again the subsets. I mean, ChatGPT effectively is the hundreds of thousands of labeling operations, where we are effectively making sure that we are satisfied with the answers and guide the ChatGPT to provide what we want. And then eventually ChatGPT start guiding itself and becoming more and more powerful. Very interesting subject. I can, as you sensed, probably talk about that well past hours. So I hope that prelude to the differences between AI and machine learning is satisfactory. But I'm quite happy to take questions and discuss further if need be.
Thank you very much. There's another question here typed in the chat. Given the size of the smart box, is it fair to assume that all the processing for ML AI happen in the cloud and not at the edge, the sensors or on board the train?
It is actually interesting, because we are driving those applications to pass as much of the intelligence onto the sensors. So edge processing is absolutely vital. And that is happening not only on the sensors, but also in the gateways. And the combination how we are continuously improving edge processing is the future power. So that's what drives the future rail infrastructure monitoring systems, which will be installed on the trains. And we are actually already doing that, absolutely. The power of allowing those sensors to do the initial decision making. When you do the FFT on those sensors, fast Fourier transform, you might be able to decide, I don't want to pass that information further to the cloud. Obviously, cloud becomes much more powerful. We've got almost infinitive processing power and time to do that. On those small sensors, we don't. We need to be very selective because they are powered by very small batteries, and the life of those batteries is always limited. 3 to 5 years is a lot, but there is a problem that if you have so many thousands of those sensors, very soon you start replacing the batteries in each of those, which becomes a problem in its own right. So we are very careful and very particular, trying to minimize the amount of processing, but make it very clever, so we take the best advantage of the battery life.
Thank you for that. Just if I may, to kind of follow up on that response. Like you said, I mean, power is one thing. Also, in terms of just processing capability and the scalability, if you have a lot of these smart book sensors on board that you're collecting, aggregating that data on board, does much of that processing, you kind of mentioned the gateway. Do you have products that that help with that, as in, for that onboard processing? That intermediate, or I guess the processing on the edge that selectively then pushes information back to the cloud.
Exactly. That is exactly the point. Yeah, I was trying to at least make that there is a combination of the two. Yeah, of three. There is a cloud processing, obviously edge processing in the gateways. And also processing directly on the sensors, and making the best use and the best combination to minimize battery life and maximize the processing power and the speed of processing is the trick. So that is what we are obviously concentrating on.
Thank you. And I'm assuming transmission dynamics has components for all of these, right? The sensors, and you also have the compute capability through your product portfolio that you can install on the trains.
Exactly. Yes, that's what we are doing. I mean, maybe that didn't come across clearly in that presentation, but that is exactly what we are doing. We've got the processing within the accelerometers, pre-processing. We've got decision-making in the accelerometers. Do I transfer data or not? Do I do the FFT? And then is the FFT looking good or not? And then we have exactly the same within the gateways or cameras. And eventually we send the data to the cloud. And sometimes we send the raw data to the cloud as the heartbeat. We strongly believe that we can't miss the raw data and then transfer the raw accelerations, raw information to the cloud for the future generations. There will be clever people coming, or more clever, coming in not too distant future, and the use of the data, which is continuously collected and becomes a powerful database for future even further improvement of the edge processing is implemented.
Thank you. No, important point about not losing all the data that is collected.
Absolutely. We intentionally transfer the raw data occasionally as standard, making sure that we don't just trust the sensors themselves, because we need to have visibility how they operate and continuously improve the operation. And all of it we do in-house. So we are not using third parties. We are developing sensors in our labs. We are prototyping, manufacturing, writing software, firmware for all those applications. Global Data Network is our own product. We don't use third-party cloud for data storage, documentation, and processing in cloud. It's all done under one roof.
That's fantastic. I have a question following up with the cloud here. Randy Mitzelfeld is asking, how do you detect and prevent external intrusion of your own train on train network? What is the state of your cybersecurity?
Yeah, I mean, cybersecurity obviously is absolutely fundamental here. One could argue that some of those systems are not critical for a train operation. We just learn what the systems are doing, but that is changing. That is changing to the point that the camera, for example, we manufactured this Pandas Vision is now ADD ready. What it means is that if we decide that the auto drop was activated and the pantograph went down because of ADD deciding that there is a sudden drop of pressure in the pipe running under the carbon, then we are synchronizing that event with the camera, and we are informed by the ADD that there has been the ADD activation. So we can concur. We can decide whether this is legitimate or not legitimate ADD activation. If we see that there is no trace of carbon missing, we don't take action. And vice versa. We may find that there is a large carbon chip missing and the ADD was not activated, and we will force the ADD to lower the pantograph. This is safety implication, because at that point we are interfering with the train operation, and that's where the cybersecurity is absolutely vital. So we've got all the mechanisms implemented, from the Bluetooth communication, TIP protocols and the chips, to the firewalls and the encryption. We are strong believers that we can when we should make our encryption, which is responsible for cybersecurity, as the mandatory, because then we don't care which route the data is transferred, whether this is via Bluetooth, via the Ethernet, or via VPN, but the properly encrypted data is actually secure. And that's how we do that. So yeah, I mean, cybersecurity, that one slide which was presented showing the system infrastructure, was actually addressing that too.
Thank you very much. We keep having more questions. We are close to wrapping up our session. So I'd like to ask Jarek and Jenny, if you can stay a couple more minutes to answer these questions. In those who have to leave, perhaps can check with the recording afterwards. How do you feel about that? I know it's evening over there.
Well, I'm quite happy to stay as long as needed. Absolutely.
Perfect. So let me remind everyone before we continue with these last couple of questions, if you have any questions about the upcoming Rail Day or the upcoming webinar for next week on construction planning for rail with CGI digital twins, please email us at info@traccs.ca. Now going back to the questions, sorry about that. We have here a question from Luke Lambert. How accurate is the system at measuring contact and messenger wire heights? Has the system ever been installed on a maintenance vehicle rather than an LRV?
Right, the accuracy of the wire stagger and the height is plus minus 20 millimeters at the moment. So whilst it may not be classified as laser precision accuracy, it is fulfilling the tasks, because we are detecting the deviation from the baseline. So I hope that answers the question. Regarding the second part, the installation, at the moment, all those systems which we installed are installed on the running trains, both on the light trains, trams, and also high-speed trains across the globe.
Fantastic. So there's a note here, wire heights and also stagger. That's a note from Luke that he put after.
Yeah, I think that's part of the previous question, the accuracy related to wire stagger, the measurement, and also pantograph height. Just as a side comment, again, it may have not come across very well from the slides, but we do exactly the same technology deploy on the third rail. So on the shoe gear, we provide the accelerometer and measure the accelerations when the shoe gear goes on the ramp, off the ramp, and seeing the joints. Again, exactly the same technology services the third rail operation.
This has been incredibly informative, and I have some praise here for you. They're saying, congratulations for mastering the subject. It's only matched by your contagious passion for the subject, and thank you. They are saying thanks for this informative and great presentation. We are very happy that you were able to take the time, Jarek and Jenny, to introduce all these details about the technology you're developing. This is so key for innovation, and we're very grateful to you. So yeah, Luke is also thanking you for your detailed answer.
Andrea, sorry for dropping a comment here. I mean, it was a massive privilege to attend TRACCS conference last year. I've been personally there, and it's been a very interesting event, and I can also congratulate you guys for organizing that. In fact, that was the time we met Daniel Lanois, who is online here, and Daniel, ex-Bombardier, now ex-Alstom, is actually representing transmission dynamics in both Americas. So clearly that kind of collaboration and that kind of the displays and conferences are very fruitful. Daniel is online, so Daniel, maybe I can pass over for 1 or 2 comments from yourself.
Yes, hi everyone. So like Jarek mentioned, I joined the team, the TD team, a year ago. And when I met and I saw the product, I was quite impressed. And so now I'm helping TD to deploy those sensors, not mostly North America, but I'm also helping for some car builders, which I would not name, but I retired from lately. And so I'm also available to answer all kind of questions, how to deploy, use them on any kind of trains, locomotives, high-speed train and LRVs. So working with the team, so we have expertise on installing those on real applications. And we're also eager to find new applications as they come to us.
Fantastic. Andrea, over to you.
Thank you so very much, Jarek, Jenny, and Daniel. We are really grateful for you and your participation. And as I said earlier today, we have an upcoming webinar next week, also in connection to digital technology and what's happening with the newer technologies. So for anyone who wants to register for next week's webinar, Construction Planning for Rail with CGI Digital Twins, Dr. Ben Guy from Urban Circus is going to make a demonstration of what digital twins can do for your projects. So you can register at traccs.ca/digital twins. This will be at 5 p.m. Toronto because they are based in Australia. So unfortunately, we couldn't keep to our noon schedule. And as I said, too, we have an upcoming Rail Day that's going to be bigger. It's going to be indoor, outdoor. We're going to have conference rooms. And we're really proud of what we're accomplishing by connecting people, having these conversations like today, where we talk about innovation and how we can do better as an industry. So I encourage you to connect with Jarek and Jenny. On screen, you have their contact information. I will, of course, email this to you as well. And we welcome any other expert in the industry who would like to present a webinar like they did. This was brilliant. It's going to be hard to follow. So thank you very much. And we hope that you have a wonderful rest of your day. And, well, a good evening to you from the UK.
Thank you very much, Andrea. And thank you very much, everybody, for attending.
Yeah, thanks very much. Great session. Nice to meet you all.
Thank you.
Thank you. Bye-bye.
Thank you.
Bye.
Bye-bye.